June 1972. Inside the thick concrete walls of the Pierrelatte uranium enrichment plant in France, the air was thick with a palpable tension. This was no ordinary factory. It was the beating heart of the French nuclear program, one of the most heavily guarded sites in the world at the height of the Cold War. Long, sterile white corridors seemed to stretch to infinity, their silence broken only by the low, steady hum of thousands of centrifuges spinning at supersonic speeds, performing an invisible dance to separate precious atoms. Everything here, from the air pressure to each speck of dust, was controlled with an almost absolute precision. In this world of order and accuracy, H. Bouzigues was a priest of the daily ritual. He was an analysis technician, one of many in white lab coats, tasked with ensuring the purity of the nuclear faith. His job, though repetitive, was of vital importance. Every day, he received uranium ore samples from mines around the world with which France had partnerships, and placed them into a complex machine called a mass spectrometer. This machine did not look at the stone. It looked into the very soul of matter, measuring the precise ratio of uranium isotopes. For Bouzigues, the numbers were truth, and there was one number in particular, a sacred constant in his world: 0.7202%. That was the ratio of uranium-235, the fissile isotope in all natural uranium. This number wasn't just an industry standard. It was a cosmic constant. It was the same in every ore deposit on Earth, in the moon rocks brought back by the Apollo astronauts, and even in ancient meteorites that had traveled for billions of years through space. It was an immutable signature of the solar system. On a Tuesday morning, Bouzigues received a new ore sample. The label read, Oklo, Gabon, a mine located in a remote West African nation. He performed the procedure as he always did. Prepared the sample, loaded it into the machine, and waited for the device to print out its numbers. The paper slowly slid out. He glanced at it, and then froze. The number was wrong. The mass spectrometer reported the concentration of U-235 as 0.717%. Bouzigues' heart skipped a beat. He looked at the number again. 0.717%. The difference might seem insignificant to a layman, just 0.003%. But in his world, this was an anomaly of seismic proportions. It was as serious as an astronomer discovering that Jupiter had shifted from its orbit, or a central banker finding a counterfeit gold bar in the National Reserve. A deviation, no matter how small, could mean only one thing. This sample had been tampered with. Someone, or something, had taken a portion of the U-235. Skepticism set in. Perhaps the machine was faulty. He carefully recalibrated the mass spectrometer, a time-consuming and laborious process. He ran the sample again. The result was the same, 0.717%. He took another sample from the same Oklo shipment. The result did not change. A cold drop of sweat ran down his spine. This was not a technical error. The problem was with the uranium ore itself. The alarm was raised, not with bells or sirens, but with an urgent phone call. Then a closed-door meeting. The news spread to the highest levels of the French Atomic Energy Commission, CEA, like a silent shockwave. In soundproofed offices in Paris, top scientists and security officials were confronted with a terrifying scenario. The only hypothesis, the most logical one, was also the most alarming. U-235 is the key ingredient for making nuclear bombs. Its depletion in natural ore could only mean that someone had built a secret facility, extracting this isotope right at the African mine. Was some nation secretly developing a nuclear weapons program right under the world's nose? Or had a terrorist organization acquired the technology to enrich uranium? For the powerful men in that room, this was no longer a scientific anomaly. It had become a matter of national security. a potential geopolitical crisis. A secret and urgent investigation was launched immediately. The objective was clear: find out who stole the uranium and what they did with it. None of them could have suspected that the answer would not be found in intelligence reports or satellite photos. The answer had been buried in the earth for 1.7 billion years, waiting to be discovered. The case of the missing uranium had begun, but it would lead them to a truth more astonishing than any conspiracy theory they could have imagined. The alarm from H. Buzig's laboratory triggered a massive investigative machine, one that operated in silence, but with absolute urgency. At the center of that machine was one man, the physicist Francis Perrin, High Commissioner of the French Atomic Energy Commission, CEA. Perrin was a brilliant scientist, a sharp mind accustomed to pondering the mysteries of the subatomic universe. But now, he was forced to play a different role, that of an international detective, and his case could determine the balance of world power. The pressure was immense. If some nation, or a non-governmental organization, had found a way to secretly enrich uranium, the nuclear arms race had just gained a new, unknown combatant. Perrin's task was not just to solve a scientific puzzle. He had to hunt down an atomic ghost before it could trigger a global catastrophe. The first step in any investigation is to eliminate the simplest possibilities. Perrin ordered a comprehensive and uncompromising review of the Pierrelatte plant itself. Was there any chance Buzig's mass spectrometer had been contaminated by samples of spent uranium from within the plant? Was there some procedural error that had altered the sample's composition? Dozens of cross-checks were performed. Standard uranium samples from around the world were analyzed to recalibrate the machines. Top technicians were summoned. The result, after days of sleepless work, remained unchanged. The Pierrelatte plant was clean. The problem was not with the measurer, but with what was being measured. The problem was in Oklo. The next step was inevitable. They had to go to the scene. A team of France's leading geologists, chemists, and nuclear engineers was assembled. Their journey was not a simple business trip. It was an expedition to a remote region of Gabon, a West African nation where the Oklo mine was hidden amidst dense forests and hills. They brought with them the most advanced portable analysis equipment, with a single mission: to take samples and find the truth. Upon arrival, they were faced with a raw industrial landscape set against wild nature. They began their work systematically, drilling into the ore veins at different depths and locations, carefully labeling each sample. The initial atmosphere was one of intense focus, but it quickly shifted to one of growing concern. On-site analyses confirmed the worst. The U-235 deficit was not only real, but it was concentrated in certain areas of the mine, designated as reaction zones. In these zones, the U-235 concentration was even lower than the 0.717% that had first raised the alarm. As the scientists compiled the data, a frightening figure emerged. An estimated 200 kilograms of uranium-235 had disappeared from the ore. 200 kilograms. The number echoed in the secret reports sent back to Paris. It was enough to build half a dozen Hiroshima-sized nuclear bombs. The atomic ghost they were hunting was no longer a hypothesis. It had left a massive physical footprint. The investigation seemed to have hit a dead end. They had confirmed the theft, but there was no sign of a culprit. There was no evidence of a secret mining facility. No trace of complex extraction technology. Everything looked completely natural. It was at this moment that the investigation took a decisive turn. Instead of focusing only on what was missing, a clever scientist suggested they look for what was in excess. The logic was simple. If a nuclear reaction had occurred, it must have left a trace, just as a fire leaves ashes. They began to analyze the chemical composition of the ore in the reaction zones more thoroughly, and they found it, the ashes of an atomic fire. They discovered the presence of isotopes of elements like neodymium, samarium, europium, and ruthenium. The strange thing was that the ratio of these isotopes was completely different from any natural ore ever known on Earth. To understand the significance of this discovery, imagine breaking a uniquely patterned ceramic vase. Even if you only find the smallest shards, an expert can look at the glaze color and pattern lines to determine exactly where the vase came from and when it was made. It's the same in nuclear physics. When a U-235 atom undergoes fission, is split by a neutron, it doesn't just release energy. It also breaks into smaller atoms, known as fission products. Each type of fission reaction produces a set of shards with a distinctive, unmistakable isotopic fingerprint. The neodymium and ruthenium isotopes found at Oklo had the exact ratio, the characteristic fingerprint, of fission products from U-235. There was no longer any doubt. The chemical evidence proved irrefutably that a large-scale nuclear fission reaction had taken place right there, in the ground. But this discovery opened up an even greater paradox. A nuclear reaction, but no explosion. The toxic fission products were not dispersed into the environment. They lay neatly contained, perfectly trapped within the crystal structure of the ore and the surrounding clay layers, as if they had been carefully stored in a secure vault. They had moved only a few centimeters from where they were created over the course of nearly 2 billion years. Perrin's team now faced an absurd situation. They had found evidence of a nuclear crime, but the scene was impeccably orderly. They had found the ashes of an atomic fire. But that fire seemed to have burned slowly, under control, and then extinguished itself. The hunt for a secret nuclear power had ended in confusion. They had found evidence of a reactor, but no builder. They had found traces of an advanced technology, but that technology seemed to be older than humanity itself. They had gone looking for a modern-day ghost, but instead, they had found an echo from an unimaginably deep past. In the meeting rooms in Paris, a heavy silence fell. All rational hypotheses had been eliminated. All that remained was the impossible. And amidst the impossible, an idea began to germinate. An idea that at first sounded insane, ludicrous, but was the only one that fit all the evidence. What if they didn't need to look for a culprit? What if the reactor was the mine itself? The air in the meeting room of the French Atomic Energy Commission, CEA, in Paris, had grown heavy. Outside, the city bustled with its usual rhythm. But inside this soundproofed room, time seemed to stand still. On the table lay stacks of reports, isotope analysis charts, and geological maps of the Oklo mine. Every investigative path had led to a dead end. Every rational hypothesis had been ruled out. They had found evidence of a nuclear fire, but no trace of an arsonist. A collective, baffled silence hung in the air. Among the most brilliant minds in France, no one could offer an explanation. And then, in that stillness, an idea was voiced. Perhaps it was whispered as a joke at first, a desperate witticism. Perhaps it was spoken by the physicist Jean-Paul Neuilly, a man who dared to think beyond conventional limits. What if we don't need a culprit? The entire room turned to look at him. What if the reactor was the mine itself? Another moment of silence, but this time it was the silence of astonishment. The idea, initially, sounded utterly ludicrous. A natural nuclear reactor? It was impossible. A nuclear reactor required incredibly complex technology, precisely enriched fuel, a moderator system to slow down neutrons, control rods to prevent the reaction from running away, and a sophisticated cooling system. It was the pinnacle of 20th century engineering. To suggest that nature, by chance, could create such a complex machine sounded like something out of a science fiction novel. Skepticism was plain on many faces, but Francis Perrin, the head of the investigation, did not laugh. With his deep understanding of the fundamental principles of nuclear physics, he did not dismiss it out of hand. His mind began to race through the variables, the equations. He set aside the preconceptions of technology and focused only on the necessary physical conditions. Gradually, an incredible possibility began to emerge. He realized that, as unbelievable as it sounded, 1.7 billion years ago, the Earth might have accidentally brought together a perfect recipe, a trifecta of prerequisite conditions for a natural atomic engine to start up and run. Condition 1, the fuel must be hot enough, Perrin explained to his colleagues. Today, for a nuclear chain reaction to occur, natural uranium must be enriched. This is because the fissile isotope, uranium-235, makes up only a tiny fraction, about 0.72%, of natural uranium ore. The vast majority is uranium-238, which does not fission easily. The 0.72% ratio is too dilute to sustain a chain reaction. However, there is a crucial fact about these two isotopes. U-235 decays much faster than U-238. This means that if we turn back the clock, the proportion of U-235 in the past would have been much higher than it is today. Perrin and his team began to calculate, and when the number emerged, the room once again fell silent. 1.7 billion years ago, at the time the Oklo rock layer was formed, the concentration of U-235 in natural uranium was approximately 3.7%. This 3.7% figure was an astonishing coincidence. It is the exact level of enrichment required for most modern light-water nuclear reactors. Nature had provided a pre-enriched nuclear fuel at the perfect grade. And the Oklo mine, by chance, happened to be one of the richest and most concentrated uranium deposits in the world. The first condition had been met. Condition 2. A break for the neutrons is needed. A chain reaction needs more than just fuel. When a U-235 atom splits, it releases new neutrons. But these neutrons are moving too fast. For them to efficiently cause other fissions, they need to be slowed down. In modern reactors, humans use substances called moderators, like heavy water or graphite, to act as a brake for the neutrons. Did nature have a moderator? Yes. And it is one of the most common substances on the planet. Water. 1.7 billion years ago, the Oklo mine was deep underground, and its porous ore veins were constantly saturated with groundwater. This water flowing through the porous sandstone acted as a perfect natural moderator, slowing the neutrons just enough for them to sustain the chain reaction. The second condition had been met. Condition 3. The environment must be clean. Even with enough fuel and a moderator, a nuclear reaction can still be extinguished if poisons are present. These are elements that are very effective at absorbing neutrons, such as boron, lithium, or other rare earth metals. If there are too many of these poisons in the ore, they will eat all the neutrons before they can cause new fissions, and the reaction will die out. Once again, Oklo was a case of exceptional luck. Geological analyses showed that the uranium deposit here was remarkably pure. It contained almost none of the elements that could poison a nuclear reaction. The third and final condition had also been met. Francis Perrin presented the complete picture to his colleagues. The pieces of the puzzle fit together perfectly. By chance. In a small corner of Africa, at a perfect moment in Earth's history, nature had accidentally combined three extremely rare factors: ideally enriched fuel, an abundant moderator, and a clean chemical environment. Nature had built a nuclear reactor. The most insane hypothesis had become the only logical explanation. The case of the missing uranium was solved. There was no secret power, no terrorist organization. There was no thief at all. The culprit was the laws of physics, and the weapon was the planet itself. The discovery of the Oklo natural nuclear reactor was not an endpoint, but a door opening into an entirely new field of investigation. The question was, no longer, did it happen? But it shifted to the more fascinating question, how did it work? The investigation transformed from a detective story into the most complex reverse engineering problem in history. The scientists were no longer looking for a perpetrator. They were trying to understand the mind of the greatest designer, nature itself. They had no blueprints, no operating manuals. Their only tools were the nuclear ashes, the fission products left behind in the ore. By analyzing the concentration and distribution of these isotopes, they could reconstruct every pulse of the ancient atomic engine. And what they found astonished them even more. The Oklo reactor didn't just work. It worked with an incredible elegance and stability. It was a perfect, self-regulating system. Its operating mechanism, as reconstructed by the scientists, followed a rhythmic cycle, like the breathing of a giant creature sleeping deep within the earth. It all began when groundwater slowly seeped through the porous sandstone layers and flooded the uranium-rich ore veins. This water acted as a moderator, slowing down the neutrons released from the natural decay of uranium. As the neutrons slowed, they were easily captured by other U-235 atoms, triggering new fissions. This new fission released more neutrons, and a chain reaction began. The atomic engine had started. For about 30 minutes, the reactor operated powerfully. Immense energy was released, heating the core of the reaction zones to hundreds of degrees Celsius. This energy was equivalent to a small power plant, all taking place silently and efficiently, deep underground. This was the genius of nature's design. As the temperature rose, the groundwater surrounding the reactor core began to boil and turn to steam. As the water, the essential moderator, turned to steam and was pushed out of the reaction zone, the newly born neutrons were no longer slowed down. They moved too fast to cause further fissions efficiently. The chain reaction was broken and automatically stopped. The reactor had shut itself down, a perfect safety mechanism to prevent a catastrophic meltdown. After shutting down, the reactor core slowly cooled. This process took about 2 hours and 30 minutes. As the temperature dropped low enough, the steam condensed back into water, and new groundwater slowly seeped back in, filling the voids. The moderator had returned. The cycle was ready to begin again. The scientists realized that this natural machine had repeated this 30 minutes on, 2.5 hours off, cycle rhythmically and steadily. It was like a nuclear geyser or a giant, natural coffee percolator. This cycle continued for hundreds of thousands of years, releasing a colossal amount of energy, but never running out of control. It was an achievement in stability that modern nuclear engineers, with all their technology and complex safety measures, had to admire. But the astonishment did not end there. As they studied deeper, they discovered something even more incredible: the way the Oklo reactor handled its own radioactive waste. One of the greatest challenges of modern nuclear energy is the problem of waste storage. Fission products like plutonium and cesium are extremely toxic and have half-lives of thousands of years. Finding a way to store them safely so they do not leak into the environment is a vexing problem. And yet at Oklo, nature seemed to have solved that problem perfectly. Analyses showed that most of the toxic fission products were locked safely right where they were created. They were trapped within the crystal structure of the uraninite ore and surrounded by impermeable layers of clay. For 1.7 billion years, despite geological activity and the movement of groundwater, these dangerous waste products had moved only a few centimeters. Oklo was not just a natural nuclear reactor. It was also the most perfect long-term nuclear waste repository ever known. It became a giant natural laboratory, an invaluable model for today's scientists, studying how to design safe repositories for human-generated nuclear waste. The investigation that began as a case of the missing had now become a lesson in humility. The scientists had come to Oklo looking for evidence of secret human technology, but instead, they found the superior technology of nature. They had discovered a machine that not only started itself, ran itself, and regulated itself, but also cleaned up and stored its own waste safely for billions of years. They had arrived as investigators, but they left as students, filled with reverence for a great engineer they had never expected. The investigation that began with a tiny anomaly in a French laboratory, a case of the missing uranium that sparked a tense global manhunt, had finally reached its incredible conclusion. There was no political conspiracy, no secret technology built by man. The truth was far more astonishing than any hypothesis. Nature had beaten humanity to the nuclear finish line. and it had gotten there nearly 2 billion years earlier. The discovery of Oklo shook the foundations of the scientific community, not because it overthrew a theory, but because it confirmed the laws of physics in a way no one could have imagined. It left a profound scientific legacy and opened up new questions for the future. One of Oklo's most important legacies is its role as a time machine for the laws of the universe themselves. Theoretical physicists had always wondered, are the fundamental physical constants like the fine structure constant alpha, which determines the strength of the electromagnetic interaction, truly constant over billions of years? Or could they change over time? Oklo provided a definitive answer. By analyzing the leftover fission products, scientists could precisely calculate the conditions that existed in the reactor 1.7 billion years ago. The calculations showed that the reactor behaved exactly as predicted by modern physical laws. This proved that the fundamental constants of the universe have been incredibly stable for at least the last 2 billion years. A crucial confirmation that underpins the entire edifice of modern physics. Furthermore, Oklo unwittingly became a giant natural laboratory for one of the most difficult problems of the nuclear age: how to safely store radioactive waste. While nations around the world spend billions of dollars designing underground repositories, hoping they can contain waste safely for 10 years, nature had already done it for nearly 2 billion years. The way the clay layers and ore structure at Oklo locked up toxic elements like plutonium is an invaluable lesson. It provides scientists with a real-world model to study, helping them better understand how geological materials interact with radioactive waste over unimaginable timescales, and thus design safer and more effective human-built repositories. But perhaps the greatest legacy of Oklo lies not in the answers it provided, but in the new questions it raised. If a natural nuclear reactor could form in Gabon, are there other natural reactors on Earth, buried deep underground, yet to be discovered? Are there geological hotspots on our planet that we cannot yet explain, which are in fact the traces of other ancient atomic engines? And the question extends even further, beyond our own planet. The conditions for the formation of the Oklo reactor, while rare, are not necessarily unique in the universe. Could this phenomenon occur on other planets? As our telescopes scan the skies for signs of extraterrestrial life, perhaps we should not only be looking for organic molecules or radio signals, perhaps we should also be looking for unusual thermal signatures, or the characteristic spectra of fission products in the atmospheres of exoplanets. A natural reactor could be a massive energy source, potentially creating a warm and energy-rich environment for life to develop in places we once thought impossible. Let us return to the image of the Oklo mine today. It is no longer an ordinary quarry. It is a monument, a natural wonder of physics, protected as a World Heritage Site. It is a humble reminder that, no matter how great human intellect may be, we are merely newcomers in a universe that is operated by complex and elegant rules long before we appeared. The story of Oklo teaches us that the greatest mysteries do not always come from distant stars or other dimensions. Sometimes, they lie right beneath our feet, written in the language of stone and atoms, waiting for a curiosity, a timely question, to be discovered. It is a testament that the universe is full of surprises, and that the laws of physics, in their infinite creativity, can produce machines more complex and wondrous than anything we can imagine. Thank you for taking the time to listen and to watch today's story. And of course, as always, a massive thank you. Thank you to everyone who supports the Science Stories channel. Whether you just watch the videos, leave a comment with your own theory, or share this story with others, I truly appreciate that contribution. The world is full of mysteries, waiting to be explored. Always keep an open mind and never stop questioning. I wish you all the best, and I'll see you in the next episode.